Okay. Someone has a question? Go ahead. All right. Now, the recordings are posted on our Blackboard page under announcements. Okay. No problem. Okay. Okay. So let's start with a review of what we did last time. All right, so we were discussing predicates and quantifiers. All right. We discussed propositional functions. P of x, okay. And we talked about quantifying propositional functions. All right, so we talked about the universal quantifier. And the existential quantifier. All right. So a universally quantified statement is the statement for all x p of x. Okay, and existential is the statement there is or there exists an x such that p of x. Okay, and any sentence that is similar to that is also, we said, either universally or existentially quantified, depending on the expressions used. Okay, so for every, anything like that is universally quantified. There exists, there is, there are some. Anything like that is an existentially quantified statement. Okay, we talked about when such statements are true and when they're false. Okay, we talked about negating such statements. So we talked about negating quantified expressions. Okay, and that basically covers what we discussed last time, right? Remember, we also said that quantified statements in logic always have to have a domain. You have to know the set of possible values for x, right? If there's no domain, then the sentence does not make sense. Okay, so there always has to be a domain. Okay, you change the domain, you could change the truth value of the quantified expression. Okay. All right, so any questions or any homework questions you would like to go over? All right, let me take a look at number 7a. Uh, 7a. In section 1.4, you're referring to 7a? Oh, I assigned 7? I thought I specifically did not assign 7 yet. Okay. If I did assign, yeah, I didn't think I did. I did not yet assign 7. All right. I was planning on assigning it after today. So, okay. All right. Okay, so let's see. 13C was requested next. Yes, we're going to be continuing 1.4 today. We're going to finish it and move on to 1.5. Okay. Okay. All right, so let's see, 13C. So in section 1.4, 13C. The question says, determine the truth value of each of these statements if the domain consists of all integers. All right, so the domain is a set of integers, and you're given the existentially quantified statement. There exists an n such that n equals negative n. Okay, right. So this is saying their existence, our domain is the integers. This is the sentence: there exists an integer such that there exists an integer n such that n equals negative n. Right? Let me just write that down this one time. There exists an integer n such that n equals negative n. Okay, is there such an integer? If we can find an integer, then this statement is true. Yes, there is such an integer, 0, as you said. Okay, in the comments here. All right, so there is such an integer, n equals 0, right? If that's the case, then n equals negative n. So because such an integer exists, it's a true statement, so it's true. Okay, so the truth value is t for true. All right, next question. Let's see here. 21C, let me take a look. Okay. So 21C, you were asked the following. For each of these statements, find a domain for which the statement is true and a domain for which the statement is false. And C, the statement is every two people have the same mother. Okay. So if your domain, let's say, is all the students in this class, then that statement would be false because not everyone in this class is a sibling, right? If I made my domain a set of brothers and sisters, right, a set of brothers and sisters from one family, then every two people from that domain would have the same mother. So if they're full siblings, at least. So in that case, the domain would be true. The statement would be true. Okay. Let's see, what else? Yes, we are going over homework questions. All right. 17 E and F. Let me take a look. All right, so 17 says, suppose that the domain of the propositional function p of x consists of the integers 0 through 4, 0, 1, 2, 3, and 4. Write out each of these propositions using disjunctions, conjunctions, and negations. Okay, so 17, you asked for which ones? E and F? Yeah, okay, let's do E. Okay, so the domain consists of 0, 1, 2, 3, and 4. That's our domain. Okay. And I'll put it in braces there. When we get to sets and set theory, we'll see we list sets by putting them in braces. Okay. Okay. So E is the statement, it is not the case that there exists an x such that p of x. Okay. So if we take just this part without the negation, let's do that first. There exists an x such that p of x. All right, that's equivalent to, we said last time, when you have a there exists, that's the same thing to doing a disjunction over all the elements in the domain. Okay, so this is the same thing as saying p of 0 or p of 1 or p of 2 or p of 3 or p of 4. Okay, now if I add in the negation here will be the same thing as this thing with a negation in the front. All right. And now if you want, you can distribute the negation if you want to. The only thing is you have to use De Morgan's law. So this would be the same thing as not p of 0 and not p of 1 and not p of 2 and not p of 3 and not p of 4. Okay, so, and that's how you would write it out. And it's a similar idea for F. Okay. Next, somebody asked for 35F. In the 7th edition here, 35 has only 3 parts, A, B, and C. Okay. Okay. All right. Any other questions you would like to go over? Okay. All right, so let's now pick up where we left off. All right, our quiz is going to be on Wednesday. Okay, it'll be on Wednesday. Let's pick up where we left off. All right, so as I said before, we're going to continue in section 1.4, and then we will move on to 1.5. So we're still in 1.4, predicates and quantifiers. Okay, the quiz is going to be on Wednesday. It will cover up to and including everything in section 1.4. Okay, so anything we do in 1.5 will not be on the quiz. All right. Okay. I will discuss it again a little more at the end of class. Okay. Somebody says they can't see what I'm writing. Do you see my screen? Maybe try pinning my screen so that I'm there in the front. All right. Okay. All right. Let's continue now, and we can discuss the quiz more at the end of class today. Okay. All right. Okay. So predicates and quantifiers. I want to now discuss translating sentences. Okay. Translating sentences from English into logic expressions using quantifiers. Okay, so I'm going to discuss translating from English to logic. Okay. All right. So let's say we have a sentence that looks as follows. We'll start with the universal quantifier here. Okay. Let's say I give you a sentence. Every student in this class has studied calculus. Okay. Here's a sentence in English. Okay, so if we want to translate this into a logic expression, let's say a question asks you to translate this into a logic expression using any of the logic symbols or operators, okay? First of all, you have to notice that this is a quantified expression. How do I know it's quantified? Because it has the word here, every, right? Every, for all, anything that's a statement about an entire set is a universally quantified statement, all right? So this is universally quantified. Okay. Once we notice that something is universally quantified, okay, we know that this is going to be a quantified expression. So the first thing we're going to do is we're going to rewrite this sentence so that the universal quantifier is clearly seen, right, in the standard form, in the for every or for all form. Okay. So let's start by doing that. Okay, so rewrite the sentence so that the quantifier is clear. Okay, so I'm going to rewrite this as for every student in this class right? That student has studied calculus. Okay. All right, so this sentence is now in a more of a standard form, the form we were discussing last time, right? This is in the for all x, right? For every, that's the universal quantifier for all or for every. The students in this class, that's our domain. That's going to be our variable x, right? The domain. Okay, that tells us our domain. For all x, that student has studied calculus. That's going to be our propositional function. Right, that's going to be our p of x. Okay, so I wrote it out in a more standard form, so we can clearly see where what the quantifier is, what our variable or our domain is, and what the propositional function is. Okay, so what I'm going to do now is, before I write this out as a logic expression, I'm going to rewrite the sentence one more time so that I see the variable in the sentence. Okay, so rewrite the sentence with the variable. Okay, and when you do this, also make sure that the domain is clearly stated. Not every time will a sentence clearly state the domain. So if it doesn't, you put the domain in there. So rewrite the sentence with a variable. I'll put in parentheses here. Make sure the domain is clearly stated. Okay, so let me rewrite the sentence with the variable. I'll introduce the variable x. Okay, so we're going to write for every student x in this class, x has studied calculus. Okay, so x is our variable. It represents a student in the class. Okay. All right. I can now write this out as a logic expression. This is the sentence for all x, p of x. Okay. Where p of x is the propositional function x has studied calculus. And the domain is the set of students in this class. Okay, so here is my sentence as a logic expression. And remember, you also have to clearly explain what the domain is and what our propositional function is. Okay. All right, questions on that? Okay. All right, let's try another example now. Let's say I asked you to express the following statement as a logic expression. So express the sentence, some student in this class has visited Mexico as a logic expression. Okay. All right, so this time we first start by identifying, again, we identify the quantifier if there is one. Here I see the word some. Some is the clue here that this is an existentially quantified statement, right? There is, there exists, there is some, anything like that. So some tells me that this is existentially quantified. Okay, so I'm going to again rewrite the sentence in a more standard form so that the quantifier is clearly expressed. So rewrite the sentence so that the quantifier is clearly expressed. Okay, so sum becomes there is or there exists. Okay, there is a student in this class such that, right, again, I'm writing it in the standard form. Remember, in standard form, it's there exists an x such that p of x. Okay, so there is a student in this class such that that student has visited Mexico. Okay. All right. Next, I'm going to introduce a variable. And again, here the domain is clearly stated. The domain is the students in this class. Okay. So I'm going to introduce a variable here. Okay. So introduce a variable. Right. So for the subject of my sentence. Okay. So I'm going to rewrite this as there is a student X in this class such that X has visited Mexico. Okay. Now, after doing this, I can write this out as a logic expression. There is, that's the existential quantifier, a student X in this class, that's my variable, right? It also tells me my domain, such that X has visited Mexico. That's going to be my propositional function. Let's call it Q of X. Okay. So this is the statement. There exists an X such that Q of X, where Q of X is the propositional function, X has visited Mexico. And the domain is the set of students in the class. Okay, so again, I just told you what my propositional function is, what my domain is. Okay, those have to be clearly explained. Okay. One more example here. We can also mix our quantifiers with other logic expressions. We've already seen we can mix them with negations. We can mix them with other things. Conjunctions, disjunctions, and conditional and biconditional statements can also be mixed with quantifiers. So let's say I gave you the sentence, every student in this class has visited either Canada or Mexico. Okay, and I asked you to translate that into a logic expression. Okay, so here this is a quantified statement. Again, it's the universal quantifier because I have the word every. But there's also a disjunction here. Or, that's a that's a disjunction. Okay. All right. So again, I can do the same thing I did before. I'm going to rewrite the sentence so that I can see this is in standard form, so I can see the quantifier clearly. And I'm also going to introduce a variable at the same time. Okay. So for every student X in this class, X has visited Canada, or X has visited Mexico. The words for all represent the universal quantifier, but so does anything that means the same thing. Okay. If I say every, for all, for every, those all mean the same thing. That's all the universal quantifier. Okay. So for every, for all, those are all the same. All right. When we discussed this briefly also last time, if you look back in the notes from last time. Okay, anything that says that or anything equivalent to that means that the sentence is universally quantified. Okay, so for every, that's universal quantifier. Here's my variable x. X has visited Canada. Let's call that r of x. X has visited Mexico. We said before that's q of x, I think. Let's keep it like that. So this would be the statement. For all x, r of x, or q of x. Okay, this would be my answer here. And again, I have to tell you the domain, where the domain is the set of students in this class. And my function r of x represents the sentence x has visited Canada. Q of x is the sentence x has visited Mexico. Okay. And as you can imagine, you combine all these different expressions in logic, you can get very complicated sentences, you can get very complex logic expressions here. Okay. Sometimes there's more than one way to express a sentence in English as a logic expression. So if you don't always get the exact same answer, that's fine. They probably are equivalent. It's just sometimes there's more than one way to write it. Okay. Okay. For the next two examples, I want to discuss restricted domains. Okay. All right, so if you look back at our first three examples there that we just did, when I asked you to express the sentence or the statement as a logic expression, I did not tell you what domain to use. We were able to just decide the domain on ourselves based on the sentence, right? We looked at the sentence and decided what the domain should be, right? What domain made the most sense. Sometimes, however, the problem will tell you what domain to use, but the statement itself uses a smaller domain or a restricted domain. Okay, in that case, we sort of have to adjust the way we write the sentence. Right? So let me explain with an example, and I'll explain as we go through it. Okay, so for a restricted domain, it's going to work slightly differently depending on which quantifier you're using. So let's start our first example here with a universal quantifier. Okay, so let's go back to the same sentence we had originally, except this time I'm going to say express the statement. Every student in this class has studied calculus. Where the domain consists of all people. Okay, so here in this problem, we want to express this sentence as a logic expression. And we're told in the question the domain is going to be the set of all people. Okay, so we're given what the domain should be. Okay, now the domain that we're told to use is different than what the sentence is talking about. The sentence is not talking about all people. The sentence is only talking about a restricted, a smaller, a subset of that. It's talking about the students in this class. Okay, so we're going to have to restrict our domain when we write this sentence. Okay. Okay. So the given sentence is talking about a subset of the set of all people. Okay. So we will need to restrict the domain. Okay. So this is what we're going to do. We're going to start by rewriting the sentence so that the given domain is clearly expressed. Okay. So rewrite the sentence so that the quantifier and the given domain are clearly expressed. Okay. Now, in order to do this, all right, what we're going to also do is we're going to use a conditional statement here, and I'll show you how in a moment. Okay, so when using a universal quantifier, we will restrict the domain by using a conditional statement. Okay, so I'm now going to rewrite the sentence. I'm going to rewrite it so I see the given domain, and I'm going to then restrict my domain using a conditional sentence. Okay, conditional statement. So I'm rewriting it as for every student, for every person. Okay, for every person, I'll introduce the variable also now. For every person X. Okay, so notice I've changed the sentence here so that the given domain appears here. For every person X, okay. Now what I'm going to do is, in order to restrict my domain from all people to just the people I want to talk about, the students in this class, I create an if-then statement. So if X is a student in this class, then X has studied calculus. Okay. All right. So I wrote out my sentence so that the domain is the desired domain, every person X. Okay. And then how do I make X be just a student in this class? I create a conditional statement where the hypothesis is the domain in the statement, X is a student in this class. And the conclusion is the property I want that student to have, that X has studied calculus. Okay. Now I can write this out, use a logic expression. For every person X, if that's a conditional statement, if then, so I'll express that with an arrow, right? That's the arrow. Okay. If X is a student in this class, let's call that S of X. That's a propositional function. X has studied calculus. That's P of X from before. So I now have two propositional functions in this sentence. Okay, so this is the sentence for every or for all people X. If S of X, if X is a student in this class, then P of X, X has studied calculus. Okay, where S of X and P of X are the given functions. And the domain is all people. Okay, as we were asked to do in the problem. Questions on that? Okay, Let's do an example now with an existential quantifier. Yes, sure. So when we're doing this, right, we're told that our domain should be the set of all people, right? But in the sentence talks about only the students in this class. It's not a sentence about all people. It's a sentence just about the students in this class. So I start out my sentence using the domain that I was told to in the question. So for every person X or for all people X. Okay, and then I turn it into a conditional statement. So in the hypothesis, the if part of the statement, here I use the desired domain, meaning the domain in the sentence. Okay, so I want to only talk about students. So here I did talk about that. So I write if X is a student in this class. Then in the conclusion, I write what property I want them to have. So then X has studied calculus. Okay. So in the hypothesis is really where I'm restricting the domain. That's why I write down the domain I want instead of the domain that I was told to use. Okay. So if X is a student in this class, then X has studied calculus. Okay. All right, so here I could write down desired domain. And here is the property that X has. Okay. All right. So if we want, that's using a universal quantifier. If we want to restrict the domain for a sentence that uses an existential quantifier, it's a similar idea, except instead of a conditional statement, we turn it into a conjunction. Excuse me, into a conjunction. Okay. So let's see an example of that. Okay. So to restrict the domain of an existentially quantified statement, we use a conjunction. Okay, so we turn our sentence into a sentence with a conjunction. All right, so let's say I asked you to express the statement, some student in this class has visited Mexico, that statement from before. Some student in this class has visited Mexico as a logic expression where the domain consists of all people. Okay, so again, the question here is not letting us choose our own domain. It's telling you the domain should consist of all people. Okay, so we need to restrict the domain to just the students in this class, right? Because the sentence is only talking about students in this class. Okay. So I'm going to start by rewriting my sentence so that the quantifier, the given the domain, and the variable are all clearly expressed. Okay, so rewrite the sentence as a conjunction. Okay, so that the quantifier, variable, and given domain are all clearly expressed. So let me rewrite the sentence. Okay, as we said before, some is going to be rewritten as there is. So I'm going to rewrite this as there is. Okay, now again, the given domain we're told it should be all people. So I'm going to write this as there is a person X such that Okay, so we were told to use that at all people as our domain, so I'm using that. There is a person, X, such that, right? So we want to say that this person is a student in this class and they have visited Mexico. We turn it into a conjunction, okay? So such that X is a student in this class and X has visited Mexico. Okay. So now I have my existential quantifier. I have my variable X. X is a student in this class. That will be, what did we say that was? S of X. And X has visited Mexico. I think we said that was Q of X, if I remember correctly. So this would be, there exists an X such that S of X and Q of X. Okay, and again, I have to clearly explain what S of X, Q of X, and the domain all are. Well, the domain was given, so I don't have to write that down again, but S of X is the statement. X is a student in this class. And Q of X is the statement. X has visited Mexico. Okay, and again, the domain is all people. I'm not going to write that down again since we were told that that's the domain at the beginning. Okay, any questions on that? Okay, so I took my sentence. It had now two properties, right? It had the one property that X is a student in this class, and the second property, X has visited Mexico. I turned both of those into propositional functions, and I wrote them with a conjunction. Okay. All right. So that is it for section 1.4. Any questions on that? All right, we're now going to move on to section 1.5. Right, section 1.5 deals with nested quantifiers. Okay. Right. So until now, every sentence with a quantifier that we looked at had only one quantifier. However, sentences can have multiple quantifiers, okay? So whenever we have a sentence that has more than one quantifier, we say it has nested quantifiers, okay? So sentences or propositions with more than one quantifier are said to have nested quantifiers. So let's go through a couple of examples of statements that have nested quantifiers in them. Okay, our first example. Let's say I write down the following expression. For all x, there exists a y. So we've got two variables here, two quantifiers. X plus y equals 0. Okay, so that's my propositional function. Okay. And let's say I tell you that the domain for all variables is the set of real numbers. So the domain is the set of real numbers R. Okay. All right. So this here would be an example of a statement with nested quantifiers. Okay, I've got two quantifiers, I've got two variables. Let's translate this into English. What is the sentence saying? Okay, if we translate this, so let's go part by part. It's saying for all, remember the domain is the set of real numbers. So it's saying for all, or for every real number x, for every real number x, right? X and y are real numbers. Next, there exists a real number y such that, okay, right, so we have a universal and an existential quantifier here, such that what? Such that x plus y equals 0. Okay. In other words, what is this statement saying? Right? Can anyone sort of express this in a different way? What is this saying? Right? Without using x and y, right? If I tell you for every real number x, there's a real number y such that x plus y equals 0, then what am I saying? Right? This is saying what?
That all real numbers have their negatives.
Yes. I wouldn't use that language, but yes, that's pretty much what we're saying, right? In other words, this is saying, the way I would express it is I would say that this sentence is basically saying that every real number has an additive inverse. Okay, so let me write that down and then I'll explain what I mean by that. So this is saying, this is the statement basically that every real number has an additive inverse. Okay, what does that mean? Every real number has an additive inverse. Okay, meaning you take any real number x, there's some number I can add to it to get 0, right? So as you said, take, let's say, for example, number 3, add to it, it's negative 3, and I get 0, right? That's called the additive inverse, right? An additive inverse of a real number is the number I have to add to it to get 0. Okay, so the additive inverse of -2 would be 2. All right, why? Because their sum is 0. Okay. As a side note, 0 is called the identity for addition, right? 0 is the identity for addition of real numbers. Okay, what does that mean? In mathematics, we always call a number an identity if it doesn't change the value of other numbers when we combine them. Okay, so in addition, when I add 0 to something, that number doesn't change. So therefore, 0 is called the identity in addition. Okay, in multiplication, which number is the identity? Yeah, exactly, 1. In multiplication, 1 is the identity because anything times 1 remains unchanged. Okay, so when we talk about an inverse, we're talking about the number that I add or multiply by in order to get the identity. Okay. All right, so this is sort of a way in logic to express all of that simply. This is how I would say every real number has an additive inverse, right? For every real number x, what does that mean? It means for every real number x, there's some real number y that I can add to it to get 0. Okay. Example number 2. Let's see another example. Let's say I write for all x, for all y, x plus y equals y plus x. Right? That's the sentence for all real numbers x and y. Right. I could say for all real numbers x, for all real numbers y. I'm just going to sort of do a shortcut and combine that into one expression. For all real numbers x and y, x plus y equals y plus x. Which property is this? This is which property for addition? Again, let's say the domain is real numbers. Yeah, that's the commutative property of addition. It's stated as a logic expression. Okay. So that's commutativity. Okay, so this in other words says that all real numbers commute over addition. It's the commutative law for addition. Okay, that the order of addition doesn't matter. Okay, I could also have more than two quantifiers. I could have three quantifiers. For example, I could write for all x, for all y, for all z, x plus y plus z equals x plus y plus z, where I move around the parentheses. Okay, and again, let's say the domain is the set of real numbers for all my variables. Okay, what property is this for? This is which property for addition? Yep, associative. That's right. Okay. Let's see another example here. Let's say I write down for all x, for all y. X is greater than 0 and y is less than 0 implies that x times y is less than 0. What is that statement saying? If you were to translate this into an English sentence. Again, let's say the domain is R. What is that sentence saying? If I ask you to translate it into a simple English sentence. Okay, so it's saying for all real numbers x, for all real numbers y, if x is greater than 0 and y is less than 0, then x times y is less than 0. In other words, let's see what we have here. Yeah, in other words, a positive times a negative real number is negative. Yeah, exactly. Okay. In other words, so and it says a simple sentence is saying a positive real number multiplied, or the product here. Let me write it this way. Sorry, I'm just going to rewrite it. I'm going to write it this way. The product of a positive and negative real number will be negative. Okay, and again, there's multiple ways you could write it out as an English sentence. Okay. All right. So we could use, as I said, multiple quantifiers here. We can throw in a bunch of different math and logic expressions. We could use this for English sentences as well, not just for math expressions, as we saw just a few minutes ago when we were just using one quantifier. Okay. I should also point out that the order of quantifiers does matter sometimes. It matters if I have mixed quantifiers. So if I have a universal and existential quantifier mixed, if I have both of them appearing in a sentence, if I change the order, I'm going to change the meaning of the sentence, okay? So when quantifiers are mixed, their order matters. Okay, let me demonstrate this with an example. Let's look at two quantified statements where I'm going to change the order, okay? So let's say I write the sentence, for all x, there exists a y such that x plus y equals 0. Okay, that's our sentence from before. All right, and again, let's say the domain for both of these statements is going to be a set of real numbers. Okay, let's say my second statement is there exists an x such that for all y, x plus y equals 0. Okay, so I switch the order of the quantifiers. All right, so my first sentence is the sentence for every real number x. Let me just write it out. For every real number x, there is a real number y such that x plus y equals 0. Okay. And let me write out this second sentence here. There is a real number x such that for every real number y, x plus y equals 0. Okay. So here I have two sentences. They seem very similar, but I switched the order of the quantifiers. The first sentence is the sentence for every real number x, or for all real numbers x, there is or there exists a real number y such that x plus y is 0. Is the first sentence here true or is it false? Okay, so is the first one. Let's call this number 1 and this one number 2. Is number 1 true or is number 1 false? It's true, right? That's the one we were discussing before. It's very much true. Okay. All right. Okay, it's true. Take any real number. Yeah, take any real number. I can add another real number to it in order to get 0. Okay, just add its negative. What is the second sentence true? The second sentence is the sentence, there is a real number x such that for every real number y, x plus y is 0. Is that statement also true or is that one false? Right. Right, F, because I know it's a trick question. Right. Right. So yes, it is. This sentence actually happens to be false. The second one here, it is false. But let's try and understand why it's false. Okay, this second one is false. Okay. This sentence is saying what? We have to go in order. That there is some number. There exists some real number out there. I don't know what it is. Such that for every other real number y, if I add the two together, I'll get 0. Okay, so did you follow that? We're saying that there exists some real number x. I don't know what that number is, but there is some real number that no matter what I add to it, the sum will always be 0. Is there such a number? And if so, please tell me what it is. Right? There is no such number. There is no such number that no matter what I add to it, I'll always get 0. But that's what this sentence is saying. Okay. For every, right? It's for every. Okay. Any is a little ambiguous, but I mean for every, right? So there is no such number, x, so that for every real number that I add to it, I'll always get 0. Okay. Right. I'm sorry. I'll try and stay away from the word any because any can sometimes be ambiguous. Right. All right. Right. All right, so in other words, what this thing is saying is that there's some number x that no matter what I add to it, I'll always get 0. For every real number y, when I add y to x, I get 0, right? So if I add 1, I'll get 0. If I add 2, I'll get 0. If I add -1, I'll get 0. If I add a half, I'll get 0. That's what this is saying, that there is some number x that for every real number y, if I add that number y to x, I'll get 0. There is no such number x. All right, so therefore this statement is false. Okay. All right. Any questions on that? Okay. All right, so again, when they're mixed, the order matters. If they're not mixed, if you have all universal quantifiers or you have all existential quantifiers, then the order doesn't really matter. You can move around the order of the variables or the order of the quantifiers. It's the same thing. Okay, one more thing I'll point out for today is that negations can move across nested quantifiers, just like they did with just one quantifier. It just changes the quantifier, right? So if I've got a negation of, let's say, there exists an x such that for all y, for all z, p of x, y, z. Okay. The negation can move across all the quantifiers. It just changes them in the same way we did it before. So this is the same thing as saying for all x, there exists a y, there exists a z such that it's not the case that p of x, y, z. Okay. So negations can move. All right. Any questions on that? All right. We're going to stop here for today. Let's now discuss the quiz. Okay. So again, just a brief discussion, and then I'll take questions. Okay. So the quiz will be Wednesday. It will be at the end of class. It will be available on Blackboard. All right, I'll create a section for quizzes on Blackboard. So when you log in on the side, you'll see a tab for an option for quizzes, and the quiz will be there. Okay. Most of the questions it'll be a mix of questions. Some might be multiple choice. Some might ask you to type in your answer yourself. Okay. Some might be true, false questions. There'll be a mix of different types of questions probably. How much time you have, I don't have an exact time yet. I'll let you know before, because I might still edit it a little bit. Okay, the quiz will cover only up to 1.4. So whatever we did today up to 1.4, and that's it. Okay, it won't include anything in 1.5. All right, is it going to be hard or tricky? There might be a mix of questions. Some might be easier, some might be a little more challenging. Okay. All right.
Professor.
Yes.
How long will we have for the quiz?
So I'm going to give you some time at the end of class to do it. Like I said, I'm not 100% sure how much time I'm going to give you yet. It'll probably be somewhere between like 15 to 30 minutes, something like that. So hopefully not too long.
Okay, thank you.
Okay. All right. I'm not going to require you to have your cameras turned on for the quizzes. Okay. We'll just do that for the exams. All right. I think somebody asked that before. All right. The answers, like I said, it will probably be a mix of questions. So some of them will be multiple choice. Some will probably be true, false. Some of them might ask you some of them might ask you to input an answer. Okay. And again, I might still change it around a little bit. So. Yeah, for the exams, you're going to have a camera on so I can proctor you. Okay. How many questions will be there? And not that many. We'll see. Even if there's a lot of questions, there'll be ones that are pretty quick to answer. Most of them. The quiz, yeah, that's fine. You can access it however you can. If you have a Blackboard app or something like that on your phone, you want to do it that way. That's fine. It doesn't make a difference. Some of the questions will be multiple choice, yes. No, you don't have to have your camera turned on for the quiz. Yeah, it will be during class time. Okay. Any other questions? Yeah. Okay, let's do the attendance now. That's a good idea. And we will end for today. What will it focus on? Everything from 1.1 through 1.4, including 1.4. So everything we've done so far. Okay, except for what we just did now in 1.5. That will not be on the quiz. Okay. Okay, so again, everyone, let me know you were here. For practice, you can go over the notes, you can do the homework questions, and if you want, you can look through the textbook and do any other questions that are in there in the sections as well. Okay. All right. If you want, you can re-listen to lectures as well. Okay. All right. Is that it? Any other questions? Last call for questions. Okay. All right. If that's all, I think we can head out. These recordings are all posted on Blackboard under announcements. Okay. I will try and have the homework up today, as well as this recording. I'll try and have up by the end of the day. Okay. Okay. All right, everybody. Any other questions? Yeah. Okay. All right. I'm going to head out, everyone. Thank you, and have a good day. Take care.